So it's a great pleasure to welcome Theodore Kolokolnikov, who is currently the Killam Professor of Mathematics and Statistics at Dalhousie University. So Theo was an applied mathematician in the real broad sense. He got his PhD in 2004 with Michael Ward at UBC. And then since then, his sort of career has skyrocketed and he's made really important contributions to pattern formation. And his work was recognized with the Kames-Pims Early Career Award in applied mathematics and several other honors. And so he'll talk today about sort of timely talk on saturation and S-I-R model.
Okay, thank you so much. It's an honor to speak here. So this is kind of a little bit of work in progress, but my general theme is going to be agent-based models, and this is kind of timely. That something I've started doing about a couple of months ago. Okay, so what is S-I-R model? It stands for S is susceptible, infected, and recovered, right? It's a system of ODEs that is the most common and one of the most basic models for modeling disease outbreaks. And basically, the susceptibles become infected when they encounter an infected individual, right? So they're removed from susceptible class, the minus sign here, and they go into the infected class, and then the infected with some rate gamma recover. So R stands for recovered, or die. So in that case, they're basically removed from the system. So R is often stands for removed, either recovered or dead. So here's some data from the US showing the number of infected individuals in red here. And this R is the recovered plus dead individuals, okay? And the question is, does this very simple model say anything about the reality? Can it actually sort of be fitted to some real world data, okay? Well, one thing we can do is we can take this first equation, right? And we can solve for beta, right? So then beta would be S prime over SI over here, right? And okay, so of course beta is, in this very simple model, it's constant, but we don't necessarily, I mean, we're not going to assume that it's, in fact, it's not going to be constant, right? Because the real world is much more complicated. There's all sorts of all sorts of interventions that change the rate beta, okay? But at any rate, given this data, we can just simply plot this beta. If we think of it as a function of time by just, taking derivative. So you have this data for S, you take the derivative numerically, find out differences, and you can just plot, okay? And it's similar with gamma, right? So here we solve for gamma, gamma is R prime over I. And so here's what happens when we do that little exercise, okay? So here I have three graphs. This curve is beta as a function of time, the red one. And the blue curve is gamma, the recovery rate, okay? And so what can be seen is that this rate gamma is roughly constant. It doesn't change very much with time. It's kind of a physical constant. How long does it take for a person to recover or die? And it's roughly like 2-3 weeks, okay? And so gamma is 1 divided by that. So if it's, and this is roughly the parameter that is seen here. So it corresponds to what we know about the virus. But for beta, interestingly, it's not at all constant. Like it starts very high, right? And it kind of goes down with time. So this infection rate slows down with time, okay? So that's the world, the data. You can also do data for, basically it's sort of very consistent through different data sets. So here's the data from United States, the same thing, right? You get this decrease in infection rate, whereas the gamma is roughly constant. And here's the Canadian data, okay? And okay, so the other thing that we can do is this graph plots beta as a function of time. So it starts from like around 15th of March to around 15th of June, okay? But here's what we're going to do instead. Let's take this curve, and rather than plotting time on a horizontal axis, I'm going to plot I, the number of infecteds, okay? And so this is what happens for the US data. So beta initially starts like it's growing, well, let's say linearly over here, and that's what you expect. Sorry, I plot here beta times I as a function of I. So if beta was a constant, then indeed it grows linearly. But then beta times I saturates to some value after a bit of time, okay? So this suggests that there's some saturation that occurs, okay? So how can we understand this? Is this really something that, I mean, is this just a coincidence, or is this like really something that comes from modeling? Okay. So let's have a look at. So one way we can think about this is look at the agent-based models. Like instead of looking at ODEs for S-I-R model, let's look at the agent-based model. So here's the model we're going to use that somehow tries to incorporate the spatial component. Okay. So we assume there's a very simple model. We'll assume there's some infection radius R, okay, so that an individual can be infected only when it goes inside this red circle. So in this example here, there's 2 infected individuals, and yeah, and so those 4 dots are the only dots that are gonna become infected at the next time step. But they don't necessarily have to be infected. They will get infected with some probability P. So any dots outside of those circles will not get infected, but the dots inside the circles will get infected with some probability P, okay? We'll also assume that it's a well-mixed situation. So basically all the dots are just randomly thrown into the square, okay? And then infected individuals are removed with some rate. Okay. So here's what happens when I mean, this is just like a few lines of MATLAB code to program this, okay? And this is what the simulation gives you. Okay, so here in the simulation, we start at time t equal to 1 with 2 infected individuals, okay? And I think there's 200 susceptible individuals, okay? And then, so here there's some parameters. P is 0.1, that's the probability of getting infected if you are inside the circle. And gamma is 0.1, that's the recovery rate, okay? So in this first time step, you can see that green and yellow circles are the one that can potentially be infected, but P is 0.1, so roughly 10% of potentially of these dots will get infected. So you can see 3 out of however many they are, right? Roughly 10%. Of course, it's a stochastic thing, so it varies, right? But on average, 10%. So at the next time step, you're going to have how many infected individuals? You're going to have the yellow dots, that's 3, plus the 2 existing circles, that's 5 overall. And so now you get 5 infected at the next time step. And the same procedure you look at all the dots that are within the red circles and take 10% of them and make them infected. So in this case, it makes that one infected and that one, etc. And then you keep on running this, okay? The other thing that happens is with some rate gamma, some infected gets removed. So this white circle means that this infected individual is going to be removed at the next time step. So it becomes blue for removed, okay? You run the simulation and you can see that it quickly spreads like this. And then after a while, everybody returns to the removed state. So you get a bunch of blue circles again. Okay, and then so this is the graph with respect to time. The red one corresponds to the number of infected individuals. You know, you start with 2, it goes up, and then it goes down. So this is a very typical S-I-R type of graph, but this is just done directly from agent-based simulation and not an ODE itself. And notice that we have the spatial component in here, right? So what's really important is the radius of the infection. Okay. So how does this lead to saturation? Well, the key is to look at like this green dot here, okay? It's inside the overlap of two circles, okay? So when you have a lot of circles, right, at some point it saturates. It doesn't really help infection rate if you have more circles than what you have here, for example. Like think if you're in a restaurant, right? You're sitting in a restaurant with 5 infected individuals for like 3 hours, right? Or you're sitting with 10 infected individuals for 3 hours. You're going to get infected regardless, right? So having more infected individuals there, after a certain point, it doesn't actually increase your chances of being infected. Okay. And in this model, this is reflected by the fact that these circles overlap, okay? Okay, so one more thing. So once we have this curve, we can do the same thing here. We can compute beta for S prime over Si, where S prime is just the derivative of those curves, right? And this is what happens, right? Again, it's kind of the same thing that you see in the real world data where beta starts pretty large, okay? And then it quickly goes down, okay? And that's the saturation effect actually in this particular model. Whereas the beta here is just roughly oscillates around the value of 0.1 sorry, the gamma of what it's supposed to be. Okay, so let's see. So let's try to think of how we can capture sort of the mean field behavior of this model, like this, like the limit where n becomes very large. Okay, the continuum limit. Okay. So given I infected individuals, the probability of infection is P times this E, where E is the probability that you are inside one of the circles, okay? So in other words, E is like the fraction area occupied by the union of this I disks, okay? So if you have, like if I is small, right, and each disk has a small size, then the union of I disk is roughly proportional to A times I, where A is the fraction area of a single disk, okay? However, when you have a lot of circles, there's all these intersections that you need to deal with, right? Okay, so then it's no longer A times I, it's something else. So that's the key question is, what is the expected area fraction of I random disks, okay? So this is the key question. So we need to compute the expected area fraction of a union of I disks. And so here's an example of what's going on. So here I have 20 disks, okay? And there's a bunch of these intersections, right? So if I want to compute the union of this area, of the union of these disks, I first sum up all of the disks. That's this quantity here. Oh, sorry, this should be this should be I times E1 here. I times E1. It's a mistake, it's a typo, okay? But then I have to subtract the pairwise intersection of the areas, right? So I have to subtract this brown regions, okay, because I added them twice, right? But then I have to add back this blue region, right, which is the triple intersections, and then subtract the quadruple intersection, okay? So, and they're kind of like randomly independent events. So the total expected area is going to have this formula. So this should be I times E1 minus I choose 2 times E2. I choose 2 is just how many intersections of pairwise intersections there are, right? And I choose 3 is how many triple intersections there are, etc. So minus, plus, minus, and so on. Okay. So that's the beast that I have to compute here. Okay. Okay. So now how do I compute this E1, E2, and 3? Okay. Well, E1 is just the area fraction of a single disk. Well, that's just pi r squared over like capital A, the total area of the domain. And E2 is the expected area fraction of the intersection of 2 random disks of radius A. Now, it's a calculation that you can actually do explicitly using integrals, right? So you can write this as like an iterated integral to compute this. But it turns out that there's actually an easier way to do it. So what the claim is that the expected area of J disks is simply A to the power J, okay? And that's an exact formula. Right? So we can verify this by integration, but you can also use a scaling argument. So by scaling, by taking like a to be very small, it's easy to see that ej should be like some constant times a to the j, at least for small a, okay? And now when also ej should be equal to 1 when a is all of the domain. So when your little red disk actually covers the entire domain, then the expected intersection area is just 1. Okay, and so that gives you, simply with the scaling argument, that gives you that this constant c is equal to 1. So finally, we have this formula for the expected area of the I disks is this sum, and then it's actually just binomial. So we get this explicit, very simple explicit expression for this intersection. So the conclusion is that the expected area of I disks is this formula here, which for small a is asymptotic to just the 1 minus e to the, I'm sorry, this should be minus IA. 1 minus e to the minus IA. There should be a minus in here. Oops. And there should be a minus in here and in here. Sorry about that. Okay, so that's the model that we derived from, basically from the first principles, right? So here I'm not, so, and this is the exact parameters as in the simulation, as in the computer simulation, right? In the agent-based model. There's two parameters. There's the probability of infections if you are inside this radius, and A is the area fraction, okay? And also when IA is small, then again, there should be a minus sign here. Then you expand the Taylor series, you get S times I back. So this model actually looks like S times I for small number of infected individuals, right? So that's before you start hitting saturation, as should be expected. Okay, so now let's see how it compares with the actual simulations. So the simulations I've shown you in the previous slide, here it is. And here's the comparison with now this ODE, okay, okay, except that there should be a minus sign here and here. And then I solved the ODE, and that's the dashed line. It fits really well. The numerical simulations here, I have 300 individuals to start with. But even when you have 50 individuals, it fits pretty well. Okay. All right. So now let's see if this actually holds for a wider class, like for the real world data. Okay. So now what we're going to do is we're going to take that data that I showed you at the beginning of the talk. Okay. And I'm going to try to fit the solution of this ODE for some parameters. So here I rewrote this slightly. Again, I keep on missing this minus here. And essentially, n is the total number of individuals, and alpha is just this parameter related to the fraction, the area fraction. Okay, I'll mention this in a bit. But here's the model. And what I want to do is I want to solve this ODE, but I want to adjust the parameters beta and alpha so it fits the actual real world data. So the way I'm going to do this is just a nonlinear least squares fit. So I can, for any given alpha, beta, and sorry, there's also gamma, okay? I compute the solution, and then I compute this least squares, which is the difference between the real world data, IJ and RJ, the recovered and infected in the real world, versus my ODE solution. And I minimize that, okay? And it's just using this just simple minimize function from Python, okay? So the only thing to mention is that the recovered here is recovered plus the dead, and that's in this data sets that I've used is given. Okay, and an infected is the total number infected minus those that are recovered, those that are currently infected. Okay, and so I just use the Python optimize routine, and it just works. Okay, and so here is the result. Yeah, here's the result. So this is the first picture is the world data, okay, up to, all of this is up to June 13th, okay. So the infected is shown in a blue curve, and then this black curve is the fitted from the saturated model, okay. So this is matches the infected as well as the recovered individuals. Okay, this is the data, the US data also works pretty well. Brazil, United Kingdom, okay. Okay, and but it doesn't always work. So for example, here's some example where it's kind of fails, right? Well, France, for one. Well, France is there's something, we don't know, the data is kind of jumpy, so it's not clear. But Spain, okay, Spain, what happened is they've controlled the outbreak really well. They've suppressed the disease. And then so I would expect that beta is not just a function of intrinsic number of infections, but it changes with time. And here, in this case, for Spain, it doesn't really work. So let me mention, so all of these curves are like from 15 March to 15th of June, roughly. So it roughly corresponds to the quarantine period. So, so the hope is that the parameters don't change too drastically during the quarantine. Of course, they've changed drastically when the quarantine was imposed, but during the quarantine, maybe they're roughly the same. And in Spain, it doesn't quite match so well. And here is Italy. For some reason, it matches the recovered, but the I from data just doesn't match at all. And the Germany just doesn't converge, actually. I can see it's, yeah. So when the epidemic is really well controlled, it doesn't work that well. Okay. All right, so we can also look at sort of the predictive value of this. It works really well for the world, US and Canadian data, where maybe the epidemic wasn't so controlled until June 15th. And for the world data, we can fit the whole data, or we can like just use the first half of the data for training, right? So to find our parameter from the first half of the data, and then we can run simulation forward, and that's the prediction that we get, okay? For what it's worth. And the same thing for the US. This is the predicted, the prediction based on sort of the first half of the data. Okay. So now, if I try to just fit the standard S-I-R model with no saturation at all, okay, if I don't have any saturation, let's say I take the US data, it gives me kind of garbage, basically. So it doesn't work at all. So if I just try S times I instead of this saturated term, like, so S times I get this kind of curve. That's the best fit, which is kind of garbage, okay? It cannot capture the data at all. Okay. Now, in terms of the saturation, this is the saturation we've derived sort of from the first principles, from the agent-based model. But you can also try to like some artificial saturation too, like I divided by 1 plus I or something like that. And that also works reasonably well. Both of those much work better than just S times I. So the artificial sort of saturation, just phenomenological, right? It works a little bit worse than the one that we derive from the first principles. Okay, so it's about 50% worse if you look at the actual error. Okay, and here's the graph for the simulation. For the simulation, the same thing. The fitted data with the saturation, so not the fitted, just the actual data, like just the parameters of the simulation itself. The black curves matches really well with the stochastic simulation. But if I try to fit S times I to this, it cannot fit at all. So for the simulation, it's clear that the saturation actually is sort of essential there. Okay. So let me just briefly mention the effect of this on the effect of population density on this. How does this saturation depend on the population density? And that's kind of was my motivations for thinking about it in the first place, because we all know that like big cities have outbreaks much quicker, right, than sort of maybe the rural areas. So one expects that the R0, the reproduction number in big cities where there's more dense population, somehow should be larger than in the rural areas, okay? So if we start with the S-I-R model, okay, and if we compare it with the saturation without the saturation, okay? Well, for small I, this saturated model is the same as without the saturation, okay? You just Taylor expand, okay? And if you compare this to the usual way of getting the R0, okay, and you rewrite all of these parameters, the area fraction can be written in terms of the density. Okay, so the area fraction is the number of population divided by, the total area is the number divided by the density, right? And so this area fraction can be written here in terms of the density, like this. Okay, so when you write it in terms of density and you compute what R0 is, you find the following formula for R0. Okay, there's the density that goes right in there. So it's going to be the density times something, right? So essentially R0, at least for this model, scales with the density, okay? So it's proportional to the population density, at least at the onset of the outbreak. So that's the conclusion. Okay, so that's, I'll skip this. And finally, one last thing I want to mention on this model. So there's also a way to sort of think about social distancing, okay? So one could think of each person having kind of a hardcore repulsion radius. So rather than throwing a bunch of dots at random inside the square, we still will throw them at random inside the square, but we'll make sure that they're separated by some distance h, all of them separated by some distance h. Okay, and it turns out that it's actually possible to carry out the same sort of similar calculation. It gets a little bit more complicated. You get this formula for the expected area of this hardcore repulsion disks that looks something like this, but it doesn't have such a simple sort of, it's just the sum. Okay, so you can't really sum it up, but it is, you know, you can write it, at least you can write it down and you can do some simulations with that. This is an example of the simulation with the hard sphere. So this black dots are the actual radii of the people, and they never, like they can touch, but they can never intersect, right? And the red dot, the red sphere is like the infection radius, right? So like in this, for example, this black dot touches the red sphere, it can get infected, and so on. And so then we can run the simulation and just validate this formula that we've obtained for this saturation term, this kind of sum, and it works reasonably well, right? So here's the actual stochastic simulation. Then if I do the theory for the hardcore, that's this solid red line, and the theory without the hardcore, it's this dashed line. Okay, so that's all I wanted to say for this model. Sorry, should I? Okay, I'll go on to my next topic now, unless there's any questions right now.
Theo, can I just ask this, this sort of SRA model with saturation that you derived from agent-based models, is this new? Was this the first time that this model was?
I've tried to look at the literature and I haven't, I can't guarantee that it's new, but I haven't seen it.
I see, okay.
Otherwise I wouldn't be talking about it today.
Yeah, okay. Good.
Yeah. It's a relatively simple calculation, but it's somehow nice. Yeah.
Okay, it's very nice. Okay.
Okay.
So can I ask, can you hear me?
Yes.
Hi. Very nice presentation. So in your model, after each step, do you redistribute the infectious individuals through the whole space?
Yeah, that's a very good question. So yeah, that's right. So there's we don't assume any kind of Brownian motion, so it's a well-mixed situation. Yes. So I also tried to do what happens if you don't redistribute, right? So what happens if you don't redistribute the individuals? Then first the infection spreads throughout the whole box, and once it spreads throughout the whole box, then it acts just like as if you were redistributing them.
Right.
Yeah.
Okay.
But here I'm not modeling the motion of individuals at all. So it's just basically thrown at random inside the box at each time step.
Thanks.
Okay. All right. So I cannot see like hands or anything. So if there's a question, just shout it out. Otherwise, I'll go to the next topic. Okay. All right. So now I'm going to talk about another agent-based model. And again, it's about this little buggers, in this case, bacteria, but a very different one. Okay. And this one has no infection. Okay. And so this is a joint work with a student from a few years ago, an undergrad student, Paul Christopher Chavi-Wadi. Okay. So this model was introduced by a group of Levy Doron from Maryland. And so here's the model. So you have a bunch of bacteria, okay, a bunch of random moving dots, okay. And so what they do is they kind of move at random, but then there's like the switching rate. So with some rate C, they will switch direction. So the random motion is kind of like the Brownian motion, so they diffuse, right? But then occasionally, what they'll do is they'll look around within their sensing radius, okay, and then will switch the direction towards like a random bacteria inside this sensing radius, okay. So with some rate, they just move at random, and with a different rate, they do this switching where they decide to follow their neighbor, okay, within some sensing radius. Okay, so it's a very simple thing, right? And so here's a sort of a pseudocode. Again, it's like a half a screen of MATLAB code to implement this. And essentially, with some switching rate, whatever some parameter you put, rand gives you a random number from 0 to 1, and delta dt is a timestamp. And so what you do is you pick with some rate, you pick a random bacteria within the sensing radius, and you reorient your direction towards that guy. And so this is what happens. So here I have 3 different movies for 3 different switching rates. I'll play them. Okay, first of all, if you have a high switching rate, here switching rate is 3. This is a high switching rate. So what happens is they form this kind of clusters, okay? And this clusters do their thing, and then, okay, here is sped up, the simulation is sped up, and okay, and then you can see they kind of like aggregate together, right? And so you end up with this 2 clusters, right? And then you just dance around for a while. But let's see, eventually, like if we wait for long enough. Oh, yeah, there. One of that, like they got absorbed, right? In the end, you end up with just 1 single cluster, and that's kind of what happens. Okay. Now, if you lower the switching rate, so I started with the initial conditions from the previous simulation. I just lowered the switching rate, and what happens is this: they still form these clusters, but it kind of expands. Okay, you have a bigger cluster, and even for a smaller switching rate, you basically can kind of get kind of a Brownian motion, sort of uniform distribution of particles, essentially. So this is kind of like as if, of course, if there is no switching at all, they just do the random walk. Okay, so Levy and Galante, his student, they wrote down kind of an ODE model for this in 1-dimensional case. And so in 1 dimension, you have like a left moving and a right moving bacteria, okay? And so at each time step, bacteria either moves to an adjacent cell according to its current orientation with some rate, okay? And with some other rate C, it switches the orientation towards like one of its neighbors, okay? So here's how it works. So this R stands for the right moving bacteria, L for the left moving bacteria, and U is the total, left plus right, okay? So, so the right moving bacteria, this term says they come in from sort of the cell to the left of it are moving to the right with some rate A. So there's that. And similarly, currently, the bacteria that are moving to the right will move away to the adjacent cell, to the cell J plus 1, with the same rate A. So there's a plus A here and a minus rate A over here. And so this is the interesting term. Okay, so what is this? With some rate C, they switch orientation. When they switch orientation, what they do is the following. Okay, so this eta plus here is the fraction of is the proportion of the bacteria to the right of the given cell J, okay? So the bottom, you have the total number of bacteria to the left and to the right, and on the top, you have the bacteria to the right of the cell J, okay? And so what happens here is with some rate C, the people in the cell J minus 1, okay, will switch their orientation when they pick at random a guy to the right and move to the right. The rate with which they pick the guy at random to the right will be this rate here. It's proportional to the number of people to their right, okay? And so then that's how this model is basically written down. That's how to understand it. And then you have, similar for the left and all that. And so this is the ODE model, and that's kind of like the limiting model of this agent-based model. Okay, so here's a movie for some switching rate in one dimension, and here the switching rate is small. So what happens is this clusters kind of dissipate, and you end up with just a constant steady state, which corresponds to everything like jiggling around and random. So on average, basically, you have uniform distribution of particles. On the other hand, when this switching rate is bigger, then eventually you get this kind of spike kind of solutions that form. So this is just a simulation of an ODE system here. And if you wait for a while, the time here is 14,000, 15,000, right? Eventually, a single solution results, a single spike results. Okay. So it's kind of similar to what we've seen in this agent-based simulation, right? Now, it turns out that there is a nice reformulation that one can do with this. If I'm not going to go through this, but basically some specific combination of like R of J minus of J plus 1 plus R of L of J minus 1. And then U is the total number. If you write it in terms of this new variables, okay, it actually, you get a kind of relatively simple form of the equation. And now what you can do is also you can just disregard the second equation, because essentially you say U decays to, okay, so if you just assume that U decays to V, there's kind of a simplified model that you can make, okay? And the simplified model is this one, okay? It only has one set of ODEs rather than two. So instead of looking for left and right moving ODEs, we get the simplified model for just the total number of bacteria, okay? And it looks like this, okay? Okay, and actually, surprisingly, it has a nice, really nice physical interpretation that wasn't noticed by, so this is my student actually noticed this transformation. And here's a completely sort of related way, but a nicer way to think about it. Okay, so this is the simplified model that you get, and the way to think about it is that you have these terms here that are just the usual diffusion terms, right? So A is a parameter with which the stuff diffuses, and C is the parameter with which the stuff aggregates. Okay, and so you have this competition between aggregation and diffusion. Okay. And so the way to understand it is in the same way. So here you have the people, sort of the bacteria to the left of J, move towards J with this rate, and this rate is just corresponds to the fraction of bacteria to the right of J minus 1, okay, etc. So that's kind of a relatively simple model that one gets. And you can also do an agent-based simulation of this model as well, okay? And it works well. Okay, and this is kind of like the Markov chain diagram for this model. Okay, and by the way, this can easily generalize to like, 2 dimensions or general network structure as well. Okay, so now let's have a look at this system. So the first thing we can do for this system is, well, we know that there is like a homogeneous steady state. If all the UJs are equal to U, then essentially the right-hand side is going to give you 0, because these guys add up to just 1. So you're going to get C times U here with a plus sign, and then you got a minus C with a negative sign. Everything works out. So that's just a homogeneous steady state, okay? So that's a solution of this ODE. And so what do we do when we have a sort of homogeneous or like a steady state solution? Well, we look at its stability, right? So we ask, what is the linearization of this around this constant steady state? Okay. And it turns out that, okay, so you do that, you plug it in, and you get this matrix for the eigenvalue lambda, right? You get this matrix equation for the eigenvalue. So lambda is going to be the eigenvalue of some matrix, but it's going to be a circulant matrix if you assume periodic boundary conditions, okay? And then you can write explicitly what the eigenfunctions of eigenvalue actually are right here, and here it is. So lambda is just f of this. There's n eigenvalues, and you have this explicit expression for the eigenvalues, okay? You can plot that. So here is this function f of theta. And if you plot that, what you notice is that now it depends, the graph depends on the c, which is the switching rate, okay? So when c is relatively small, this dashed line, you are below 0. So this red line is 0. That's the instability line, okay? But as you increase the c, eventually there's an instability that kicks in, okay? And this instability corresponds to low frequency modes here. Theta is small, right? And the way it happens is, well, so it turns out that the derivative of f is 0 at 0. So we just have to look at the second derivative of f at 0, okay? And that's going to tell us everything about the stability, right? And we obtain this formula for the stability threshold in terms of this a. This d is just the sensing distance, okay? So it's how many neighbors you sense to your left and to your right. Okay, so the next step is to look at the continuum limit. So to do the continuum limit, we treat this as kind of a difference discretization of some PDE, okay, of some underlying PDE, okay. In other words, we just expand in Taylor series, right? So let's uj equal to some u of x and t, and uj plus k is u of x plus k times h, where h is like the spatial discretization, okay. Then to leading order, okay, we just get, okay, we have to expand to order h squared, and we just get the heat equation or the diffusion equation. Now the usual, I kind of written this diffusion equation in a kind of a funny way. Let's just say c is equal to 0, then you don't have any of those terms. That just corresponds to the usual diffusion equation. And of course you do get the usual diffusion equation. In that case, you just get basically ut is equal to h squared times a times uxx. Okay, which is sort of a forward diffusion equation. But as you increase the c, the way I've written it here, you see there's a threshold at which this bracket becomes 0. And then suddenly the diffusion equation becomes the backward diffusion equation. It destabilizes the constant states, right? This is exactly the analog of those instability thresholds that we've observed in the ODE system. They persist for this PDE. Okay, so now the next question is, well, for this diffusion, it's just linear, okay? So if we want to capture what kind of aggregations that form, that's not enough, because linear, you can't get this kind of stable aggregates in a linear equation. Everything will either diffuse or just blow up, right? Depending on the sign of this bracket. So what we do is we go to the next order. So we have to expand up to order h to the 4th, okay? And if you do that, then finally you get this 4th order ODE or PDE in time and space. Okay, so one gets this 4th order PDE. So here the way I wrote is with the minus sign, because I want the constant homogeneous state to be unstable, so I can get some spikes. Okay, and then this A is this stuff here, and then you have the 4th order term, and at the same order, this is all order h to the 4th terms, you get this nonlinear term. So finally you see some nonlinearity here. Okay, this funny looking nonlinearity is what you get. Okay, and then you have some constants A, B, and C, where you can scale some of them out. And at the end, okay, so before I do that, let me just show you the simulations. So here is the simulation of the discrete model. So here's time versus space. Okay, and as we go on, you start with like a few spikes, then you end up with just 2 spikes here, eventually with 1 spike. That's the simulation I showed you the movie of previously. Okay, then the next thing I will do is I will take this PDE model and simulate a PDE model, okay? Rather than the discrete ODE, I simulate this whole PDE, and this is what I get, right? This picture is what I get. So you cannot, by eye, you cannot tell the difference. This is with 50 mesh points, okay? And if I take a slice here at time 1500 or 15,000, then this is the circles is the ODE simulation, and the solid line is the PDE simulation. So it agrees really well. Even the position of the spike agrees as well as the profile. Okay. On the other hand, if I lower down the switching rate, then starting with some bumpy initial conditions, everything kind of converges to the constant state, right? This is also reflected in the PDE as well. And this is the sort of the snapshot. You can see the agreement of PDE and ODE very well. Okay, so one more thing we can do with this is we can scale out this constants until we get one single constant. So this is kind of, after some rescaling, we get this single PDE, right? And there's one parameter that depends on all of the previous parameters of the model, namely the sensing radius, D, the switching rate, C, as well as the diffusion rate, A, okay? All of this kind of boil into this one single parameter. So you get this novel PDE. As far as I know, I've asked a bunch of people, it seems to be a new PDE. It's kind of fourth order, nonlinear, right? So it's complicated, right? So you say, okay, so this is good. What more can we do? It's a fourth order nonlinear PDE. But there is actually something you can do, okay? So, well, you can look at the steady states, right? The spikes here that correspond to like the profile of this aggregation of the bacteria, right? Well, that corresponds to the steady state of this ODE. So you set UT equal to 0, okay? And then you get like this fourth order ODE, but then it's in a divergence form. So, and if you assume that everything decays at infinity, then it becomes this third order ODE, okay? So third order ODE, but it has the scaling symmetry, okay? There's a scaling symmetry for this. If you look at this term here, and when you have a scaling symmetry, you can reduce the order of the ODE. Okay, so if you use this scaling symmetry, make the appropriate change of variables that comes from the scaling symmetry, you end up with a second order ODE for this variable z as ux over u. Okay, now the second order ODE, what can be done? Well, you can do phase portrait analysis of this, right? You can write it like this, or you can look at like divide this equation by that, and then you get a first order ODE at the end. And this is kind of a Bell ODE. It's non-separable or whatever. So it's not clear like what can be done. But it turns out that this ODE, just motivated by doing some phase portrait and some experiments, when we plotted phase portrait, we observed that one of the heteroclinic looks like a parabola. Okay, so we tried to plug in a parabolic ansatz into this ODE, and it turns out that it actually works. There is a parabolic solution. There's this quadratic solution, very simple solution to this ODE, okay? And there's actually two of them, and one of them, you can, once you have that solution, you can untransform all those change of variables, you go back to the original variables, and you get finally the solution of the profile. It looks like sec h of x to some power, right? And so that's the final solution of the profile of the fin. Okay, and so this is the final result, which compares the ODE simulations, okay, versus this profile derived analytically, where alpha is some parameter that depends on all of the other parameters, right, for different values of C. And you can see that when this bump is, it agrees really well, right? So the agreement is especially good when it's not too sharp. When it becomes like super sharp, then it kind of loses its continuity, right? It becomes a little bit discrete here. But even then, it works surprisingly well. Okay, so so we actually have this explicit solution to this steady state that describes the profile and the extent of this aggregation. So what more can you say? Well, that's about all that we know how to say analytically anyway. You can also look at the stability of this profile, like it appears to be stable, but that's something that we don't know how to do. But you can write down the linearized problem around this profile. You get this kind of equation And at least you can solve this numerically, right? You can just discretize it and use like MATLAB to solve for the eigenvalues of the corresponding matrices. It does appear to be stable, but we don't have any. So it'd be nice to have any kind of results that's analytic about this. Yeah. So I think that's all I have time for. So I'll conclude here and I'll welcome any questions.
Okay, very good. Thank you very much, Theo. So are there any questions? Are there the first part or the second part? Maybe we'll start with the second part. Can I just ask about this? So this new PDE, you have this nonlinear term, but I mean, the fourth order is kind of like a viscosity, the fourth derivative, right? So it should somehow smooth things out. But it's fundamental to getting this excellent agreement. So if you turned off the nonlinear term, you wouldn't have gotten good agreement at all with your.
Yeah, so if you don't, you have to have some nonlinearity of some form or shape in order to get a stable solution that's not a constant, right?
Exactly, yeah.
So yeah, you'll never get a non-constant solution if you don't have nonlinear terms, right?
Right.
But this nonlinear term, I mean, it comes from Taylor series expansion, right? So it's just, you do the Taylor series expansion, and it's at the same order as this linear viscosity term.
Yeah, I guess in the sense that you have a product of the derivatives, yeah. Okay. I see. That's interesting, really interesting. Are there any other questions about either part?
I'm trying to, for some reason, it's not showing me the, oh, here, okay.
No other questions? Okay. Well, I mean, the first part really does seem to have some remarkable agreement with some rather timely, important data. So.
Yeah. So the one thing I sort of mention is so a couple of things about this. It doesn't always agree, right? And also the other thing is, one can argue that if you have enough parameters, then you can fit anything.
Fit anything. That is true.
So there's that, but yeah, I mean, I don't know. It does seem to work. I was surprised.
But the vanilla S-I-R doesn't work so well. I think you should.
No, it doesn't work at all, right? The normal S-I-R, like with the S times I term without saturation, yeah, it doesn't fit at all. Like it's here.
Right. Oh yes, yeah. Okay. Interesting. Okay, well, it's almost 5 o'clock, so if there's no other.
I have a small question, perhaps. I put that in the chat, but is there a progressive solution to your equation as well as the spike one?
Oh, so like a moving
yes,
spike.
Because the solution you have reminds me of the Korteweg-de Vries solution, and so I could hope there could be something progressive as in KDV. Do you have that or not?
Right. So, I mean, it doesn't appear to have that like from the numerics, right? It doesn't, at least numerically, you don't see any kind of moving pulses. All you see is that the pulses that are, I mean, they will move towards each other if there's two of them, right? But if there's like a single pulse, it will just stay there. Right. So it doesn't.
Okay. And you cannot prove that, because that would be an interesting result to prove, not numerically but theoretically. That means that putting a solution of the form suggested, and then C shows that there is no value of C which is suitable, except from C is equal to 0, because you have run already.
Right. So that's a good question. I haven't tried.
So perhaps that could be a good try.
But yeah, I mean, it would be interesting to try. Like, how should I say? Because I don't observe it in the numerics, like I tend to try to sort of explain things that I observe, right? If I don't observe it, then it's probably not there. And like you can try like very hard to prove it, but like it's probably going to be a wasted effort because it's probably not there.
But it's you cannot see it numerically. Perhaps you cannot tune exactly the initial value and the initial derivative so that it would get this solution.
Yeah, it's very generic. Like I try like random initial conditions, right? And it just.
Yes, but if you want to find a very precise value, then trying randomly is a little bit. You can not just reach exactly the exact value, but that's something that would be to study.
Yeah, if it does exist, it might be, but it's probably, if it does exist, then it would probably not be physical, right?
It would be not stable, perhaps.
Yeah, perhaps not stable, exactly. Yeah, but it's an interesting point.
Any other questions? Okay, then I'll thank you very much, Theo.
Okay, thank you.